Alright guys, we're back here with another statistics tutorial, again talking about confidence intervals. Now, this is going to be a slightly different scenario than what we've talked about before. Here we are given we're requested to find a confidence interval, but we're not given a population standard deviation. Okay? Before we've always known a population standard deviation, so here we don't know that. In fact, we don't know a sample standard deviation or a sample mean yet either, but we're going to have to find that. So let's see what our context is. A company randomly selected 9 office employees and secretly monitored their computers for a month. That's not so nice, but that's what's going on. The times and hours spent by these employees using their computers for non-job related activities, playing solitaire, browsing Reddit, Twitter, Facebook, etc. during this month are given below. So there's hour figures of how much time these 9 employees spent not doing what they were supposed to do on their computer. So it looks like the lowest was 1 hour in that month, the highest was 16 hours, and several in between. Assuming that such times for all employees are normally distributed, make a 95% confidence interval for the corresponding population mean for all employees of this company. So we want to find the sample mean of that sample data there and use that to estimate the population mean for all such employees. So we're going to use that estimate, but we know the estimate's not going to be exactly right, so we're going to construct a confidence interval around that estimate such that we're 95% confident the population mean is within those boundaries. So let's get with it. We always need an xbar, a sample mean, when we're doing confidence intervals. Now we're not given xbar, but I think we can pretty easily find xbar. Now remember, we're going to have to use some formulas we haven't seen perhaps in a while to find xbar and then S, our sample standard deviation. But most everybody remembers how to find the mean, just the arithmetic mean. That is, let's see here, x bar, let's fix that. X bar equals the sum of x over n. So add up all your x values, divide by n. So n here is 9. Okay, so we have 9 data points. We add all of those x values up, divide by 9. So 7 plus 16 plus 9 plus 8 plus 11 plus 4 plus 14 plus 1 plus 6 divided by 9. So I think if you add all those up, we get 76. So you add all your x values up, 76, divide by n, which is 9, sample size, and it looks like we get 8.4 repeated. Okay, we'll eventually round that, but let's leave it as 8.4 repeating right now. So there's x bar. That's one of the things we need to find our confidence interval endpoints. Now the other thing we need, or one of the other things we need, is S, a standard deviation. Again, we're not going to find sigma here because this is sample data, not population data. So S, now this one's a little more tough. We haven't seen this formula in a long time. Oh, and it's going to be a big formula. It's going to be a fraction here. Okay. Now let's talk about the standard deviation for a sample formula. Now, some classes may use the more definition type equation for the standard deviation of a sample, whereas you take the average squared deviations from the mean and take the square root of that. Okay, we use a shortcut formula in our book, and if you remember, the shortcut formula is going to be the sum of the x squareds minus the sum of x squared over n, and then we're going to divide that entire thing by n minus 1. So here, notice that these two things that look very similar are actually different. Here we have the sum of the x squareds. So we're going to square all the x values, then add them up. Here we are taking all of the x values, adding them up, then squaring them. We'll then divide by n as well. So let's see what we get here. Let's go ahead. Again, a big square root, and then a fraction. Let's see, the sum of the x squares. So we need to take 7, square it. Take 16, square it. 9, square it. 8, square it. 11, square it. Add all of those up. So when you do that, it looks like we get 820. 820. Then we're going to subtract. Now, we have already found the sum of x, or the sum of the x's. The sum of the x's were 76. So if we take 76, square it, and then divide by n, what do we get? Okay, 76 squared is 5,776. Divided by n, which is 9, and we get 641.7 repeating. Then we're going to divide by not n on the bottom. This is a sample standard deviation, so n minus 1. 9 minus 1 is 8. Okay, almost done here with the sample standard deviation. Okay, so let's see. 820 minus 641.7 repeating is about 178.2 repeating. Divide that answer by 8. You get 22.27 repeating. Lastly, don't forget to take the square root. So the square root of that 22 and change figure, and I get 4.710993 4086. Be careful here. Sometimes if you round this standard deviation too early, it's going to produce error later. I mean, this is a rounded answer here. It's rounded to what, 9 or 10 decimal places. So it's certainly already rounded. But if you round this to 4.72, if you round it to 2 decimal places, or maybe even 4.7 to 1 decimal place, you're going to really mess up your confidence interval later. So it's always better to keep a more precise answer and then round however you're requested to for your final answer. Do that at the very end. Keep as many decimal places, maybe 8 or 9 decimal places, and then round to 2 or 3, whatever the directions say, at the very end. Okay, so we have S and we have X. Okay, now let's review how to find a confidence interval. So let's go over here. Here's a new color. A confidence interval is given by X bar plus or minus. Let me make that a little better. Plus or minus. Now, when we do not know a population standard deviation, we use the t distribution. So it's t instead of z, and then times the sampling distribution standard deviation. So we know x bar, that's 8.4 repeating. Now we don't know t, and we are very close to finding the standard deviation of the sampling distribution. So let's go back over here and find that really fast. Let's see here. We know the formula for the standard deviation of a sampling distribution. That is sigma. Oh, you know what? I am using the complete wrong symbol there. We don't know sigma. Let's erase that. Alright guys, I'm going to back up. I'm going to erase this right here. Maybe some of you guys caught that and was wondering when I was going to fix it. So here we are. Going back over here, it is S sub x bar. So T times S sub x bar. We don't. This right here has nothing to do with sigma. We're estimating sigma using S. Okay, So let's go back over here and calculate the standard deviation of this particular sampling distribution, and that is given by S sub x bar equals, it's S divided by the square root of n. Okay, so we found S to be, I'm going to go ahead and write it out, 4.7199340886. We're going to divide that by the square root of n. So the square root of 9, so divided by 3, and let's see what the standard deviation of the sampling distribution is. So that's 4.71, that figure, divided by the square root of 9, which is 3, and I get 1.57, let's see, 3311362. Again, I'm going to leave it like that for the time being. You don't want to round too early. That's probably overkill right there, but better be safe than sorry. Okay, so now going back to our confidence interval over here, we know x bar, we know the standard deviation of our sampling distribution. Now we just need to find t. Now t is a little bit different to find than z. You know, the table is set up differently. Z values are based on the standard normal distribution. They're just standard deviations. They're numbers that represent standard deviations. Okay. Now the t distribution is actually more like a family of distributions. It's different. The distribution changes based on the sample size. Now the way we talk about the term we need to introduce now is degrees of freedom. Degrees of freedom can be more complicated in certain contexts using different distributions and different techniques, but for us, degrees of freedom, now we're going to abbreviate that as df equals n minus 1. So here, degrees of freedom is 9 minus, I was going to tell you the answer. 9 minus 1 equals 8. So we're going to go to the t-chart in the back of the book, and we need to concentrate on the row that is 8. So the rows are given by, are the degrees, represent degrees of freedom. So if you flip back to the back of your book, or if you have the chart in the front of your book, so I'm going to go ahead and look at this. Now I'm going to draw you a little picture here. Let's see, let's go to orange. Okay, let's go over here and talk about the t distribution. So the t distribution, at least how our table is set up in the back of the book, always is concerning area in the right tail. So let's say here, let's just say right here. Okay, when you look up t-values in the back of the book, they're always going to be give you the positive t-value that corresponds to a certain amount of area in the right tail. Okay, that's a little bit different than the z-chart, but it's not so bad to find. So now the question is, for a 95% confidence interval, what area under the curve is there going to be in the right tail? Okay, so let's talk about both tails for the time being and see if we can get an answer. Okay, we're talking about a 95% confidence interval. That means we want 0.95 area centered around our estimate. So centered around x bar. Okay. Now, if we want 95% of the area, or 0.95, centered around our estimate, what's going to be in those two shaded tails? Okay, well, what's going to be left over, since there's a total of one, area of 1 under the entire curve, it's going to be 1 minus 0.95 is going to be the amount of area in your two tails. Now that's the area in both tails together. So since this distribution is symmetric, we're going to have, okay, so let's see, 1 minus 0.95 equals 0.05 area in both tails. Okay, if you divide 0.05 by 2, we get 0.025 area in each tail. So here, that area is 0.025, and the area in this tail is 0.025. So we want to find this t-value. In fact, we can find this t-value too if you really want to. We're just not really concerned about that negative one. But we'll go ahead and find it. Okay? Now, so let's erase this question mark here and use the back of the book to find that t-value. So, the way the t-chart works in the back of your book is that you look at the column that corresponds to the area in the right tail. So we know the area in the right tail for a 95% confidence interval is going to be 0.025. And we look at the degrees of freedom row, so the 8th row. So if you go to your t-chart and look at the 8th row, and then look at the column with 0.025 in it, and you find the intersection of that column and that row, we get t is equal to 2.306. So 2.306. Now it actually turns out that since the t distribution, just like the z, is symmetric, it's approximately normal, symmetric, so the negative, the t value over here that has a, that refers to the area in the left tail of being 0.025, that t value is going to be, I ran out of room there, negative 2.306. But we're concerned about the positive one here, because that way we always use the positive in our confidence interval expression, because you want to find the margin of error by multiplying these two terms, and you want the margin of error to be a positive number. So, okay, so that's the t value you want. It's 2.306. So now, if I go back over here, we can actually find, our final solution, find the endpoints of our confidence interval. So let's go over here and get our solution. So what's x bar? X bar we found was 8.4 repeating. Let's go ahead and just round that. Oh, let's go to 3 decimal places for the time being. So 8.444. Then we have plus or minus. Now, the next part of our expression is t, which we found was 2.306. Okay, and then we have our standard deviation, which we found, let's go ahead and we can round this to 3 decimal places too while we're at it. So 1.573. Okay? Now, just like when we did confidence intervals before, this product right here, the figure that you're adding and subtracting each time, that is E. E. So what we're really doing here is taking our mean, which is 8.444, adding and subtracting E. Now, what is E actually equal to? Well, let's see. That 1.57 figure times 2.306, our T value, and we get E is equal to 3.628. So E, remember E is margin of error, is E is 3.6208. Okay. Now to find the endpoints of our interval, all we have to do is this calculation twice. Now remember, I keep comparing this to the quadratic formula because that's another example you guys are familiar with when you see a plus or minus. So there's actually two solutions embedded here. One, the upper endpoint, is the solution when you add 3.628 to 8.444. The other is when you subtract 3.628 from 8.444. So let's first find the upper endpoint. 8.444 plus 3.628, and I get the upper endpoint is 12.07 if we round our final solution to 2 decimal places. Now, the lower endpoint is 8.444 minus the margin of error, which is 3.628. And we get 4.81. Oh, if I round to 2 decimal places, that is 8.2. So there is our confidence interval. Now let's actually write that in interval notation. So remember, you write in parentheses for interval notation 4.82, comma 12.07. Now, what does this mean? This means going back up here to our context. We found a sample mean, and that sample mean time represented the average time 9 employees spent doing non-work related activities on their computer. So we used that sample mean of 8.4 to estimate the population mean for everybody in the company. Okay, but we know that unless we get very lucky, the true population mean is not going to be 8.4. It'll probably be close, but it won't be exactly. So we construct a confidence interval, and here it is a 95% confidence interval, such that we are 95% certain that the true population mean will be somewhere inside our interval. So somewhere between 4.82 and 12.07, and these are hours per month. We're 95% confident that the true population mean lives in this interval. Okay. In other words, if we took every possible sample of size 9 out of everybody that worked at this company, 95 times out of 100, the sample mean would live in this interval. So 5 times out of 100, of course, it wouldn't be on average. Okay, that's what the interpretation is here. Again, we're using sample data to estimate a population parameter. We used xbar to estimate mu. So we're pretty sure with 95% certainty that mu is somewhere between 4.82 and 12.07. Now, just like before, we could, let's say the margin of error was too big. So the margin of error here, you see, is 3.628. If the margin of error was, for whatever reason, decided to be, too large, that doesn't seem so important. Looking at this context here, we're just talking about the amount of time people spend on their computers not doing what they're supposed to. But in certain contexts, a margin of error of 3.628 might be very large. If you're talking about margin of error when time is super important, or you may be talking about things to do with medicine and so forth. You might want a small margin of error. That's all. How big or small the margin of error is tolerable is all to the context. Let's just say that for some reason we wanted a smaller margin of error. Okay. Again, this is going above and beyond the current exercise you just worked. So we're done with the solution that we need for this particular problem. But let's just say we wanted a smaller margin of error for some reason. If we wanted a smaller margin of error, we learned previously that you have to, or one way to decrease the margin of error is to increase the sample size. Now, another way to decrease the margin of error would be to decrease your confidence, but you don't want to do that. Okay, so let's see what happens if we increased our sample size. So we only took 9 employees. Okay. Should we go ahead and do this? Well, yeah, sure. We'll make a couple assumptions, but we'll go ahead and do it. Let's say we increased our sample size and still had the same sample mean. So let's say, let's go over here and let's pick a new color. Since this is new stuff, let's say that we n equals 100, and then all else is the same. Now that is all else that can be. So that is x bar equals 8.44, but and s equals, what did we say it was? 4.7199348086. So let's say we had a sample of 100, and again, we're making assumptions here, but we have the same sample statistics, x bar and s. Well, watch what happens to our t-value and our standard deviation, and then so what happens in consequence to our margin of error. So let's find first the standard deviation of the sampling distribution. Watch what happens to that. That's s sub x bar. Well, remember, it's s divided by the square root of n. So it's 4.7199348086 divided by the square root of 100, which is 10. So you get 0.4719934086. Okay? So you see right off the bat that our standard deviation of the sampling distribution, let's see, it's reduced by about 1/3. Okay? So that's going to make the margin of error smaller, since that's one component of the margin of error. Now let's see what happens when we look up our t-value. Because remember, t-values change depending on your sample size. So degrees of freedom here is n minus 1, which is, let's see, 100 minus 1 equals 99. Now, if you go over to the back of your book, at least in our book, now if you're working on a different textbook, you might see something different, but if you look in the back of our textbook only has degrees of freedom rows to 75. And what we have to do is, if you have degrees of freedom greater than 75, you have to use the very last row, which has an infinity symbol where the degrees of freedom are, which you use if your degrees of freedom are greater than anything listed in the chart. So since that's the case, we're going to use that last row. And so using the last row, and the area under the curve is still going to be 0.0025, but let's see what the t-value is whenever we have a higher sample size. T, looking at the 0.025 column, is going to be 1.0 960. Okay? See how our t-value decreased. Okay, 1.960. Our t-value decreased because we had a higher sample size. So if we construct the confidence interval now, we have all the parts we need. X bar, which is 8.44, plus or minus t, which is 1.960, times our standard deviation, which is 0.4719034086. That second term there is our margin of error, so 8.44 plus or minus e, which is the margin of error, and we get, let's see, 1.960 times 0.4719934086. If we round this to maybe a couple decimal places, we get 0.925. We can do 925. So that is E, our margin of error. So our two endpoints, upper and lower, 8.44 plus 0.925. Let's see, 9.365. And then the lower endpoint, 8.44 minus 0.925, and you get 7.515. So that interval is 7.515 to 9.365. Okay? Now see how much E changed here. E went when we had a sample size of 9 at 3.628 hours. When we increased to a sample size of 100, we got a margin of error below 1. So we decreased the margin of error by, let's see, about, maybe, a little over, between 2.5 and 3 hours. Okay? Yeah, so that was, a significant decrease. And again, depending on your context, you may or may not need a smaller margin of error. So, just like before, the moral of the story is if you need to decrease the margin of error, and that is without decreasing confidence, because we're still at 95% confidence here. We didn't decrease that. So the only other way to decrease the margin of error is to decrease your confidence, but we don't want to do that, so we increase the sample size and we get a much smaller margin of error. So, again, just to summarize, talking about companies, employees, and how much time they spend not doing the work they're supposed to, we constructed a 95% confidence interval around those 9 data points. We found that by finding the standard deviation and xbar from our raw data. We then found the margin of error, constructed our confidence interval here, and then we went further than that and said, what if we increase the sample size, left everything else the same, increased the sample size, made a few assumptions, but we demonstrated that you could reduce the margin of error greatly by simply increasing the sample size. That is, we went from a margin of error of 3.628 to a margin of error of 0.925, and that was due to increasing sample size to 100 from a sample size up here of 9. Okay? Alright, so I think I've talked about everything I can in this example. If you need any help beyond this, certainly feel free to always stop by my office or shoot me an email, and we'll get you all the help you need to get whatever straightened out that you're having confusion about. Alright, you guys have a nice weekend. See you next week. Need help? Let me know.